Thank you very much, Vishal. So I'm going to talk about simple models of a particular problem in global warming, that is of cumulative emissions accounting. But before that, I'll kind of set the stage for thinking about cumulative emissions accounting, and then talk briefly about the broader context in which the present push and movement towards decarbonization has to take place. Okay, so how many of you know what a well-mixed greenhouse gas is? What do you think is a well-mixed greenhouse gas? Let's take some examples. Is carbon dioxide well-mixed? Is it well-mixed? Yes? Yes? How many say yes? Yes, okay. N2O, nitrous oxide, well-mixed. Say it has an atmospheric lifetime of 120 years. Is it well-mixed? Yes, yes, okay. Methane, what's the atmospheric lifetime of methane? 30 years. Yeah, about a few decades, right? About 10 years, 10 to 12 years. So does that make it well-mixed? Does that make methane well-mixed? How many say yes? How many say no? Yes? No? Okay, so evenly divided. It's also well-mixed. Ozone, is ozone a well-mixed greenhouse gas? No. All right, so a well-mixed greenhouse gas is basically something which you can assume to a first approximation is uniformly mixed throughout the atmosphere across both hemispheres. So the basic comparison is between the lifetime, the atmospheric lifetime of the gas, and the interhemispheric mixing time, which in models ranges between a year or 2 years. All right, so methane, carbon dioxide, carbon dioxide with a lifetime of several hundred years, methane with a lifetime of about a decade, right? Nitrous oxide, about 100 years. Yes, ozone, of course, no. All right, but not all well-mixed gases, as we will see, can be compared by their cumulative emissions. So there's a different comparison at work, and we'll see that. So here's a diagram from the most recent IPCC report. Observe warming a bit over a Kelvin. And as you can see here, in order to compare warming, you have to compare averages with averages because of interannual variability, even in the global mean surface temperature. Much of that comes from human influence. Much of the human influence comes from well-mixed gases, and it's partly offset by the effects of aerosols. All right. Here's a schematic of the global carbon cycle with everything you've learned in the last week. Some of this should come together for you. The reds show the fluxes, the blues show the pools. A petagram of carbon, this is carbon, right, in CO2. This is the mass of the carbon atoms in CO2. 1 petagram is 1 gigaton, all right? So emissions right now are closer to 10 petagrams. This diagram is about 10 years old. So in the next diagram, we'll see the emissions will be a little more. And then some of it's taken up by the surface ocean. It's taken up in photosynthesis. Photosynthesis is balanced partly by respiration in plants and soil. You see there's a bit of an imbalance, right? So the soil and plant respiration doesn't add up to photosynthesis. That imbalance comes from excess CO2 in the atmosphere, all right? So there's little more photosynthesis than there is soil and plant respiration. Similarly, there's ocean loss and ocean uptake. There's little more ocean uptake than there's ocean loss, and that imbalance also comes. Imbalance in the fluxes also comes from the effects of excess CO2 in the atmosphere, right? So the air-sea exchange equilibrium has been influenced by the effects of excess CO2 in the atmosphere. From here, you can see also the pools, right? So the deep ocean, as we learned yesterday, is an enormous reservoir of carbon, but a much larger reservoir is, of course, the Earth's crust and fossil fuels and so on. There are also really small fluxes, right? Volcanoes. So if you were to ask how many years would it take for volcanoes to put out as much CO2 in the atmosphere as fossil fuel burning does, the answer is about 1,000 years, right? 0.1. So it's roughly 0.1% of fossil fuel burning. Sorry, 100 years, right? It's 1% of fossil fuel burning. There's also burial to sediments. So basically CO2 dissolves in water and in rainwater. It's a weak acid and it dissolves in sedimentary rocks, which slowly end up in the ocean. And this process will take a really long time to take up excess CO2. So the ratio of this flux to the flux of what we're putting out is 1 in 1,000. So that's 0.1%. Right? So you see there are fast processes and there are slow processes. And here we see the fast processes. There's a more recent diagram. So you see the human emissions is closer to 10 petagrams of carbon. This is the mass of carbon, not CO2, the mass of carbon in the carbon dioxide emissions. And here in red, you see the perturbations to the fluxes as a result, right? So photosynthesis has gone up by 3 petagrams of carbon, air-sea exchange, there's a net uptake by the oceans. All right? And of course, there are much larger fluxes between the surface ocean and the deep ocean, and much larger fluxes involving the biosphere as well. So a summary would be, well, there are fast and slow processes in the carbon cycle. The natural fluxes are really large. The anthropogenic emissions can be seen as primarily perturbing these large natural fluxes. But on the annual time scale, if you were to think about it, let's go back here. This is about 9, right? This excess is about 2, this excess is about 3. So 1/2 between a year to a few years, 1/2 of every 10 petagrams of CO2 that fossil fuel burning is putting in the atmosphere is being taken up either by excess photosynthesis compared to respiration, compared to the excess of photosynthesis compared to plant and soil respiration, and the excess uptake by the oceans compared to what's being degassed into the atmosphere. All right, so about 1/2, remember that number. And therefore, it should not be surprising. So this is another figure from the recent IPCC report. If you think about what's called the airborne fraction of CO2, it's roughly 44%. There's a lot of interannual variability, as you can well imagine, but I draw your attention to the main, to the black diagram, to the black curve here, which is the 5-year running mean, right? So what is it saying? It's saying that at any given time, about half of the cumulative carbon dioxide that's been burnt, that's been put into the atmosphere, that's been released into the atmosphere by fossil fuel burning, still remains in the atmosphere. And this is closely tied to the numbers that we saw here. Okay, this has consequences. It has a couple of consequences. The airborne fraction is roughly constant during the period when emissions are quite large. It's roughly, rule of thumb is about 50% of the CO2 emissions remain in the atmosphere, but the rest takes a really long time to reduce in concentrations. So here was an important paper by Archer and Brovkin called the Millennial Atmospheric Lifetime of Anthropogenic CO2. So what are they doing? These are emissions trajectories, and then they simulate what happens to the concentration of carbon dioxide and what happens to the warming. So what do you see here? The first thing I see here, it takes about 10,000 years, right? 10,000 years for this to come down, and it still hasn't come down, right? Even at the end of 10,000 years. And they have simulations which go on to much, much longer, close to 100,000 years. And here's a key message. The largest fraction will take place on timescales of centuries, but a significant fraction, the rest, remains for 1,000 years or longer. And ultimate recovery takes place on hundreds of thousands of years, a geological timescale, right? Typically associated with perceptions of nuclear waste. And so this is an important thing to bear in mind, all right? So the long tail of atmospheric CO2, which requires the slow processes to act on it, involving, uptake of the CO2 that's taken up by the surface oceans, entering the deep oceans, and other geological processes involving rock weathering and so on, take hundreds of thousands of years. So there's this long tail that one will have to live with, and that has consequences. So here's one of the set of consequences coming through the effects of slow processes in the carbon cycle on the atmospheric lifetime. Here's a diagram from a paper. There were a couple of papers published around the same time, around 2009. And what this is showing is essentially for an intermediate complexity model. Each color is a different intermediate complexity model. Each point is a different scenario, right? So they've run different scenarios with different intermediate complexity models, or rather emulators of intermediate complexity models. And for a given color, global warming is roughly proportional to cumulative emissions, right? So the y-axis is global warming, It's the peak warming. This is the total area under the emissions curve. All right. So what they pointed out was, well, how do we compare global warming scenarios, given that the carbon cycle is complex? Different models tell us different things about how sensitive the Earth system is. But for a given model, the global warming is roughly scaling with cumulative emissions. And people had this intuition well before this paper came out. This and another companion paper published by a different group in the same year, coincidentally, pointed this out for the first time, right? Demonstrated this by running Earth system models, running different scenarios and saying, hey, in these Earth system models, you can plot global warming for a given model, for a given setting of parameters. You can plot global warming against cumulative emissions and you find roughly a straight line. All right. And this gave rise to, the earliest discussions in the summary for policymakers on the importance of cumulative emissions. So the community had the intuition about the importance of cumulative emissions, but they could now point to studies that demonstrate that there's a direct link between cumulative emissions and global warming in Earth system models. So here's a quote: the ratio of global mean surface temperature change to total cumulative emissions is relatively constant, independent of the scenario, right? What are they referring to? They're referring to the fact that for a given model, it's roughly a straight line. But may depend on model, right? So, but is model dependent. And here they're referring to the fact that for different colors, each color corresponding to a different model, you might get a different slope, right? This goes back to the discussions about climate sensitivity and uncertainty in transient response across these models. But this has important implications for any given target. Higher emissions in earlier decades imply lower emissions later on, right? So if we want to achieve a certain target, we think about cumulative emissions. If we emit more now, it means we're left with less later on. And so this directly gives rise to the idea of carbon budgets. I want to make the following point. If you look at simpler models and ask where this comes from, you can think about it as arising from the fact that global warming and cumulative emissions have a relationship of proportionality. But underlying this is a much simpler fact, right? Which is also true in, say, a simpler two-box energy balance model that Anshuman described. Okay, so you're not going to get linearity, right? These are not straight lines. Unlike here, these are straight lines. But you still get the same underlying behavior, all right? You have different emissions trajectories which do a variety of things. You can even take a trajectory where the emissions comes down, goes back up again. Who is to say that we'll the first time we decarbonize, we'll continue to be successful in maintaining a low carbon economy, right? But even if you then, for that scenario, you plot global warming versus cumulative emissions, they all line up. Okay, so here's a more general feature of Earth system models and even simpler models and two-box energy balance models. Okay, so as long as you have something like this, this would work, right? Is that clear? Everyone with me on this? Yeah.
After how many years is that plot made?
Which
equilibration plot?
This one?
Yeah.
This is not after how many years. I'm taking the temperature trajectory of this, okay, and I'm taking the cumulative emissions trajectory of this, plotting it. I get a curve. So at every time, at every point in time. Yeah?
So it's equilibrating very fast.
There's no equilibrium held. So equilibrium has not been reached. This is the transient response is path independent. It's not that the equilibrium response is path independent. So the point being, carbon budgets stem from the fact that the transient response itself is path independent, right? So we're not saying at equilibrium, there will be a relationship between the total CO2 you've emitted between pre-industrial times, however you define it, and then at equilibrium, and the equilibrium warming. We're saying this is a property of the transient response. Yeah, is that clear? Yeah, that's an important clarification. So the idea is very simple. You have emissions trajectories. Corresponding to it, you'll have a time trajectory of warming, right? I plot the area under the curve at every time, right? So it's the integral of the curve as a function of time. Yeah, that's on the x-axis. On the y-axis, I run it through the two-box model, and then I get temperature as a function of time. That I plot on the y-axis. They all line up. Okay, so it's a very simple feature of the Earth system, which is much more model independent. It's even true of the more complex models which have proportionality. These are actually intermediate models. I wouldn't say that these are the most complex models, but it's also true of the simplest models, which are the two-box models which capture this.
Just to clarify.
Yeah.
In the previous figure, can you tell me which model is the white one?
Which is the white one? Yeah, that would be the mean across the ensembles. Yeah. Yeah. Yeah? Yeah, I don't see a white one here. Yeah. Okay, clear? Clear on this, what the figures are showing? So it's a much simpler idea, very much simpler fact that is enough. And so the point is, when you use simple models in policy, you want to use simple models to essentially explain only the most simple and robust facts that are enough for your decisions, right? Yeah. What is to say that, you know, this proportionality comes from some cancellation of feedbacks, and turns out 10 years later, we find all the models are missing feedbacks? Will it undermine all this IPCC's discussion of cumulative carbon budgets? No, right? Because this IPCC's discussion of cumulative carbon budgets is founded on a much simpler fact, right? Which I will show to you comes from a vast separation of timescales. Okay, one timescale which is a property about our world and our society and our history in the world. One timescale is a property of the climate system. It's the separation between these timescales, which is very robust, which gives rise to this. All right. So a point, just to give you an illustration of the use of simple models in policy analysis, this kind of analysis, you have to ask, what is the relevant fact about the problem, and how do I explain that fact in a model-independent way? So this is one illustration of that. And the idea is, it comes from a very simple feature. It comes from the fact that we discussed earlier, there are slow processes in the carbon cycle. That we can be sure about. Models may differ in details of terrestrial feedbacks and details of ocean biogeochemistry and consequences for the carbon cycle. They will not be wrong about the fact that there are slow processes in the carbon cycle, which lend multi-century lifetimes to atmospheric CO2, which is much longer than another time scale we described. Okay? So if I were to eliminate, and just to make this concrete, if I were to eliminate those slow processes in the carbon cycle, let's say I were to pretend that CO2 behaves like methane in the atmosphere. I don't change anything else. It still has logarithmic forcing and so on. But pretend that CO2 has a 12-year atmospheric lifetime. What happens? Well, the global warming is not as large because CO2 does not accumulate in the atmosphere, right? But also you see, if I were to attempt to reconstruct the same figure, I cannot. Right? Global warming versus CO2 is no longer path independent. The transient response, right? That's what we're ultimately interested in. Okay, not the equilibrium response. And the idea, this just give you a heuristic view of where this comes from. You can think about global warming in the simpler models, but also given that global warming is a function of global mean energy budgets, even in the more complex models, you can think of it as really depending on three things. It depends on time because there's a transient response, right? It's not an equilibrium response. So it depends explicitly on time. I'm not going to write down the equation, but the point is the two-box energy balance model that you saw yesterday, you can explicitly integrate it because it's linear. And then you'll see there's an integral. When you have an integral, time appears explicitly in your solution because you have the transient response. It depends on radiative forcing. What does radiative forcing from CO2 depend on? Anyone? Concentrations, right? Depends on excess concentrations. So then I can think about excess concentrations as my cumulative. I need to bring in the quantities that I'm interested in into my account of the problem. So I can write excess concentrations as my cumulative emissions times the airborne fraction, right? Which is, we know, is roughly 1/2 in the observations, right? So global warming depends on three things. It depends explicitly on time, it depends on airborne fraction, it depends on cumulative emission. So let's, for 2D purposes, so that we can render it in 2D, just illustrate the issue by comparing the effects of cumulative emissions and airborne fraction, right? So let's say I have a function of m and r. I want to then ask under what conditions is that function approximately a function of m only, right? That's the problem at all times, right? So then I have contours of my function, and essentially my next contour is being picked only by the change in m, right? I have at time t plus delta t, the next contour of my function is essentially just being picked by what is delta m in that intervening delta t, without regard to what delta r had been, in the intervening delta T, right? So essentially the change in global warming between two time steps is is approximated by what's called the directional derivative along the axis of M. That's all there is to it. And then you can simplify, this is just algebra. And essentially you get a very simple result. Cumulative emissions has to change very rapidly compared to the airborne fraction, compared to another time. We're not going to, this is damping time scale. This is a property of the climate model. I'm not going to get into this part of the story. There's an analogous part of the story here, but the part of the story I'm going to concentrate on is here, the first inequality, right? So what are timescales? Essentially, I have a growth rate. Growth rate is an inverse timescale, right? So there's another way of saying cumulative emissions grows much more rapidly than the airborne fraction changes, right? Because the growth rate is inverse time. Yeah, and the growth rate is time dependent. The time scale is time dependent, right? And so just to illustrate, in the model, if you go back to putting in the real, realistic carbon cycle, airborne fraction takes centuries to decrease by 50%. Cumulative emissions has been taking decades to double. So you have this large disparity in time scales, which is also true of the simpler models, right? And of course, the more complex models. But this comes from the carbon cycle. This comes from our emissions pathway. And so because of this, you can do cumulative carbon budgets. In the absence, like I said, if I were to make it behave like methane, then the airborne fraction decreases more rapidly on timescales that end up being comparable to methane. And so here, you can explicitly compute the timescales. You can say, well, the evolution of the cumulative emissions occurs on timescales of decades. This timescale goes up over time. Essentially, the growth rate of cumulative emissions is coming down towards the end of the emission cycle. Airborne fraction evolves, right? It takes essentially several hundred years to change by a factor of E. That's what this is saying. If CO2 were to be artificially made to behave like methane, the airborne fraction would evolve quickly. Slower than CO2, slower than cumulative emissions, but not slowly enough, right? There has to be, to have a good approximation that we can neglect the effects of airborne fraction, it would be nice to have an order of magnitude difference between these timescales, right? We often say one is smaller than the other. One can be neglected if it's an order of magnitude smaller. Okay, so one gets a very simple result in terms of the requirement to. So what's going on, right? I'm saying between this year and the next, the transient global warming depends only on how much emissions I have, right? Of course, there's internal variability. These models don't have internal variability. And we're not talking about the effects of internal variability. We're talking merely about the effects that can be attributed to the increase in CO2 between this year and the next. So this year and 10 years hence, 2023 and 2033, right? And if that scales proportionally to cumulative emissions, any fluctuations in airborne fraction in the intervening period should have no impact on, right? So essentially it boils down to saying, well, airborne fraction is changing very slowly. Cumulative emissions between now and then is essentially doubling on decadal timescales. All right, airborne fraction is changing by a factor of E on several 100-year timescales. Okay, so then it's not enough, and since there's an order of magnitude separation, I can neglect the effect of airborne fraction, say it's small. But if there isn't, then I can't, right? That's the idea. And so the thing that has to be small, the quantity that has to be small is this in the y-axis, right? For me to essentially use cumulative emissions accounting. And one can also show that this quantity on the y-axis is directly related to the quantity on the x-axis. What is a quantity on the x-axis? It's how many years over which my emission cycle plays out, right? Divided by the atmospheric lifetime. And if I want this to be, the quantity on the y-axis to be, and so emission cycles here with different shapes essentially, right? So different emission cycles with different shapes and different time periods. And then you can simulate them for a whole ensemble of atmospheric lifetimes. Turns out the height of the emission cycle doesn't matter. It's the how many years it plays out over, what its shape is. Is it sharply peaked? Is it, is it more concave? Is it more concave? Is it more convex? And so on. In relation to the atmospheric lifetime. And why is that? Because in order for the quantity on the y-axis to be less than 0.1, which is what we want approximately, to neglect the effects of airborne fraction, I want the quantity on the x-axis to be roughly less than 1, right? That's the idea. So in other words, I want my emission cycle to play itself out, go up and come down, right? roughly within the atmospheric lifetime. That's the idea. And this comes from very simple modeling. This dimensional analysis comes from very simple modeling. You can write a model for the airborne fraction, which is the excess concentration divided by cumulative emissions, from which you can compute the airborne fraction timescale. And any of you who integrated linear differential equations would have encountered, right, integrals that look like this. Yeah, so I'm just rescaling time. So just writing t over tau is t over big T times big T over tau. And so I get two things that matter. Yeah.
Again, one clarification. Can you go back to your?
Yeah. Yeah.
Here I see that path dependence. Can you scale around that? If the time if alpha is less than 1,
yeah,
are you saying it is
path independent, right? If alpha is less than 1, 10 to the power 0, then roughly this is less than 10 to the power minus 1, right? Which means the cumulative emissions growth rate is an order of magnitude larger, at least, than the airborne fraction growth rate. So the path independence phenomenon we described earlier. Yeah, is that clear? Yeah, that's an important clarification. Clear to everyone? Yeah. And so there's just simple rescaling of time. And so then you see immediately there are two quantities that are important to this discussion, right? One is alpha, which is what's the length of my emission cycle history as a fraction of my atmospheric lifetime, and where am I x, which is now where am I in vis-a-vis the emissions cycle. And so it turns out path independence gets worse and worse as you proceed, right? And that's because the cumulative emissions timescale goes up. Once cumulative emissions has grown, it's harder to grow something that's already large, right? That's the idea. When in the beginning, emissions is really small. Cumulative emissions is also really small. It's 0 over 0. But the moment emissions becomes non-zero, it becomes very easy to grow cumulative emissions. And cumulative emissions grows very rapidly. Cumulative emissions are large, and then you're decreasing emissions. You're hardly growing cumulative emissions. Then other things begin to matter. That's the idea. All right? And so then you can basically integrate these things, and you know, these are called repeated integrals. You can integrate them and get a simple formula for this. And that can actually allow you to also discover that there's a relation between this, you know, it being roughly in order of magnitude apart, and this being close to 1. Okay, so there's stuff you can do, but the point is that the story about path independence essentially then boils down to asking, how long is the period of the emission cycle in relation to the atmospheric lifetime? So can we have carbon, you know, cumulative emissions budgets for methane? No, because we've been emitting methane for several decades, right? Only if you have a new greenhouse gas, or let's suppose you had a new greenhouse gas with an atmospheric lifetime of 10 years, like methane, right? Only if the emission cycle had played out within 10 years could you have had carbon budgets, okay? We have carbon budgets for CO2 because the emission cycle is essentially playing out over a couple of 100 years, right? If you look at the CO2 emission cycle, it didn't start growing in earnest until the early 1900s. And we're thinking about scenarios where it plays itself out by the end of the century, hopefully, right? Hopefully much longer than that, but that's a couple of centuries, much shorter than the atmospheric lifetime. Okay. The thing I should say is CO2 has multiple processes, so multiple timescales, right? So the earlier calculations I showed for CO2 take into account the multiple timescales. This is just a very idealized analysis for a single time constant gas. So there's still work to be done, you know, extending this to the carbon cycle and so on. So we're barely scratching the surface of these issues, but there is a role for simple analysis. And in summary, I would just say, you know, we're talking about carbon budgets because we're talking less than a century and a half into the growth of carbon dioxide emissions, the major growth of carbon dioxide emissions, and most of the scenarios we're considering are the ones that will play themselves out over this century. If you were to imagine, and you could do this, I don't have the plots here, but very easy to generate. You could, if you generate scenarios where there's carbon dioxide scenarios were to play themselves out over the entire millennium, then you're not going to get cumulative carbon budgets, okay? Then you will not get this kind of result, okay? So it's a function of something about where we are and what our timescales are vis-a-vis decarbonization, as well as features of the carbon cycle. And just here's an illustration that, you know, if you go up the cumulative emissions timescale grows, because what is it? It's 1 over the growth rate, right? So it's 1 over the growth rate of something is the quantity divided by its rate of change, right? What is the rate of change? Emissions. So what's the time scale? It's cumulative emissions over annual emissions, right? The area under the curve over that quantity itself, right? So this grows. And so when you have scenarios which are growing and then declining, this is again to illustrate. So this is real data, and these are just scenarios, right? So real data up to about 2010. And so real data, the earnest increase around 1900s. You can approximate all of these scenarios as being ones where, right, essentially a couple of or 300 years is your emission cycle. And since the atmospheric lifetime of CO2 is longer than that, you have path independence. You start to have a problem towards the end of the emission cycle because, cumulative emissions is large, emissions are small. Okay, and so this sort of explains things. So simple models explain things. There've been studies that have shown, when you have people talk about negative emission scenarios, right? So in order to, given that we're in a world in which there are cumulative emissions constraints, and if we fail to decarbonize early enough, at some point we need to find ways to draw down CO2 from the atmosphere. And it's well known, it's documented in simple Earth system models of intermediate complexity with realistic ocean carbon cycles and terrestrial carbon cycles and so on. Case in point, the UVic, the University of Victoria model. They've done a whole bunch of studies, and the other EMICs do this as well, where you increase cumulative emissions and then you decrease it, because when emissions becomes negative, the area under the curve begins to decline, right? Cumulative emissions begins to come down. You don't have path independence, right? And the precise nature of this hysteresis is something you can only understand with the more complex models, right? With the Earth system models, which have good carbon cycle, where also the ocean circulation is a bit realistic enough to be able to capture the association between heat and carbon uptake by the ocean, which is very important to the nature of this hysteresis phenomenon. But the point is, this only becomes important when the emissions are small or negative, and we see that here, right? So if you plot cumulative emissions versus time and the cumulative emissions time scale, what's happening in these negative emission scenarios? The cumulative emissions is changing, but it's changing very slowly, right? You also see that, if you allow me to switch back and go back to an earlier plot, you also see that here. You start to see the slopes diverging at the end, right? Why do the slopes only diverge at the end? For the exact same phenomenon. When the cumulative emissions have accumulated, it's hard to grow them. So then, at this point, the changes in the airborne fraction begin to start to have an impact, but this is only consequential for cumulative emissions budgets if this process is sustained through a long period of low emissions, right? See, at this point, you see them diverging dramatically, but it doesn't matter because there's no change in the x-axis, right? So the point is, when there's a change in slope and there's a concomitant change in the x-axis, that's when you start getting into situations where you cannot, in the situation of CO2, where you nominally use carbon budgets. Here's a situation where you cannot use carbon budgets, all right? So I think that's that for this, then I think that's that. So the point is, there are things you cannot do. You can't capture this, right? You can't understand uncertainties. For this stuff, you really need the more complex models, okay? The association between how the oceans allow us to simultaneously take heat and carbon, and whether the uncertainties in the ocean, in the heat and carbon uptake by the oceans is correlated across models or not, and how it plays out in ensembles is crucial. You can't do that with simple models. But you can anticipate the problem with cumulative carbon budgets will arise with negative emissions, will arise when you have sustained phases of low emissions, and so on with simple models. All right, so there are things we can do, there are things we simply cannot do, and so we need a wide range of models, even in the context of climate change. Okay, so let me just switch gears a bit and talk a little bit about some other things. I'll give you some context for the understanding of when the climate change signal began to be observed. If you were to take a look at this figure, when would you guess a climate change signal was first observed? In the global temperature record. Someone said 60s. Did I hear someone say 60s? Around here? Maybe a little later, maybe here? Yeah, how many think earlier? Earlier? Earlier, okay, earlier. Some suggest earlier. How many think the real discussion may have begun around the 70s? Okay, all right. So I think right in different ways, just some quick history. You have access to this, so you can look at it later. I'm not going to go through every point, but following the first calculation, 1896, by Arrhenius, and the interesting observation of calendar of an increase in temperature in around 1940, right? The claim that greenhouse global warming is underway, not just the observation that temperature is increasing, but the purported link between that and and greenhouse warming. To the first calculation, many things happened, right? We're going to talk, so there are a couple of reasons to describe this. So let me maybe talk about the calendar story. The calendar story is around 1940, he observed this, right? But this was mainly due to natural variability. So the dashed lines show the effects of internal variability. This is from a paper by Wallace Broker in 1975. The CO2 effect had been quite small at that time, okay? But by the mid-1970s, when this paper came out, the CO2 effect had been much larger than the natural effect and had moreover been quite comparable to the meteorological records, okay? So that's the point, all right? So this is around here. Also, by that time, the expectations had been set because 1975, the calculations had been done. But many things had to be done between here and here, right? So you needed a computer model of the global atmosphere. You needed a detailed understanding of radiative transfer to know that it would have a significant effect on the radiative balance. You had to have the measurements and understanding of what the oceans do. Sorry. And this is work that was led by, oh, sorry, pressing the wrong button. Initiated by observations by Roger Revelle about, essentially carbon-14 in the oceans, and said, well, initially people thought, the deep oceans will just take up all of CO2 because they control CO2. But Revelle observed, well, no, so this is a very interesting story, and I won't have time for the full picture, but I think it's very interesting. You would find it very interesting to read that whole story. It was initiated by measurements of radioactive carbon-14 in the surface ocean, recognizing that it takes about 10 years. Initially, that was thought to be large. Later on, the expectation was that that would not be much of a problem because the atmospheric lifetime is small. Then it was understood that, well, that's just telling you how much is coming into the ocean. It's not telling you that, well, the same amount is degassing from the ocean and entering into the atmosphere, right? So the key quantity with respect to the ocean is how long it takes for CO2 in the surface ocean to enter the deep ocean, which is much longer. But that understanding was precipitated by the initial observations by Revelle, okay? Water vapor feedback, studies of the water vapor feedback, right? Can amplify global warming. What's the difference between water vapor and carbon dioxide? Are they the same? Can we control the water vapor in the atmosphere? How many say yes? How many say no? Okay, no. Right? So that's controlled by thermodynamics, right? So this understanding developed at this time, okay? And this culminated in the first calculation of the effect of doubling CO2. But this story is also interesting because the 1967 paper also helped us understand the vertical structure of temperature that would result, or the vertical structure of warming that would result from the effects of CO2 forcing in particular. Okay, so this we've discussed. So in the 1970s, there was a discussion about climate change, right? Just look at these quotes. World may be inching into a prolonged warming trend. CO2 may be the world's biggest environmental problems. Polar climate scientists evenly divided on warming or cooling why? Because people thought we were due for transition into the next ice age. All scientists agree new factors entered, a wild card never there before. But at the same time, this was not incontrovertible because at that time, models did not represent internal variability. And the question of the debate about fingerprints ensued through much of the 80s. Here's a quote. No one type of change is likely to convince the scientific community until well into the next century when the world it might be too late by then. The best bet for early detection seems to be the identification of a number of changes: warmer weather, warmer ocean water, cooler stratosphere. Cooler stratosphere comes from this work. Okay, the first calculation of Manabe and Weatherall. So there are some expectations of what fingerprints would look like. But there's still some work that needed to be done, increased precipitation and so on. Look at this. The approach being pursued is more like developing a composite picture of a culprit rather than arresting the first suspect who has the same color eyes. Researchers call the technique fingerprinting, although it's hardly as conclusive as the human technique. It's remarkable that people are talking about scientific data and then comparing it to human fingerprinting and making comparisons about accuracy. But it's not surprising that Hasselmann in the early 90s published this paper on fingerprints, which changed the entire business of fingerprinting. But the genesis of this actually goes back to his earlier work in the 1790s, where he spent a lot of time thinking about signal-to-noise problem. And so there's a direct link between this paper and this paper. But the idea is, and I'll give you an example of it, but without getting into the details, the idea is you might expect a climate change signal. And here you essentially, very broadly speaking, you're thinking about spatial patterns or space-time patterns as vectors in some space, right? And so the direction of the vector is just a way of saying, where is the pattern strong, where is the pattern weak? And that may not be your optimal detection direction. So essentially you're using what's called some linear combination of some weights that will project that signal into some other direction where the noise is smaller. Essentially, it's a way of smoothing the signal by giving more weight to places and more weight to those features of the problem which are less likely to be contaminated by noise. Okay, that's the basic idea in a nutshell. And I know it's not very revealing, but there might be a more apt way to describe it without doing the math. So here's an example. Here's the early Manabe and Weatherald, one of many, many figures in Manabe and Weatherald's wonderful paper, which shows when you have more CO2, and this is ppm, right? So from 150, 300, 600, note the curves shift to the left. There's cooling in the stratosphere accompanying warming in the troposphere. So this signal was first pointed by Manabe and Weatherald. It's been confirmed by observations. So here are observations of both tropospheric and stratospheric temperature measurements, models, and so on, and data. Here's a recent paper that came out that sort of brings it all together. And so people have been looking at fingerprints, applying fingerprinting in various ways, looking at, for example, where you would expect the tropospheric temperature signal to be higher. You get these, you see these characteristic spatial maps, of CO2-induced warming and how it affects the spatial distribution of temperature. But this is very interesting also because it demonstrates not only bringing together observations that confirm Manabe and Weatherald's early suggestions based on the first calculation of CO2-induced warming, but also showing that when you bring in stratospheric temperatures into your fingerprinting technique, the signal to noise ratio goes up by a factor of 3 or 4. So basically, as you have more data, your signal to noise ratio goes up. If you only include tropospheric temperatures, it's basically this bunch of curves. As you also include stratospheric temperatures, it's this bunch of curves. All right. And if you would like, better intuitions on this, I think you can do no better than checking out this very nice article that came out in 1997, written by Ramanathan. Okay. Can I take another 10 minutes, 5-10 minutes? Yeah. Okay. So then just to bring things to a close, I want to just contrast, the difference between, and I think many of you will be familiar with this. There was a Montreal Protocol signed in the 90s, which was quite successful in reducing CFCs. In contrast, when the Kyoto Protocol was signed, greenhouse gases went up, despite the signing of the Kyoto Protocol. So any guesses what the big difference is between our relative success in coalescing to respond to the, yeah, go ahead.
An alternative readily available.
That's an important point, yes. Anything else?
Recovery times being faster than
Time scales, yeah. Time scales, yeah. But what about emissions? What else drove the difference in emissions? Okay, so there's a lot of similarities, but there are also differences. And I leave this for you to take later. But I'll give you an illustration of this difference. Also limited in scope, broad scope in terms of what fraction of emissions it covered, right? Montreal Protocol covered much larger fraction of the emissions. The availability of substitutes in the latter case, or in the case of CFCs, and the widespread belief, which is not untrue at the time, that substitutes are expensive and CO2 emissions are so deeply embedded in the way we organize economies. And again, I won't, I leave it for you to look at later. But this is also manifested, right? It's exemplified by the quotes by the corresponding leaders at the time of signing of each of these. I'm pleased to sign the instrument of ratification, unanimous approval by the Senate, right? And here the Senate's vote 95-0 shows this clear consensus, it's unfair and ineffective means of. So this contrast is also very apparent. But in the meantime, so I think a striking feature of, to just give you some broader context, of the last 20, 25 years has been, there's been a growing disparity between our success and our ambition, right? So we're not doing much of recalibrating our ambition and toning it down to be more commensurate with success. And that's because there's been a lot of really important climate science that's come out between 97 and 2015. And my end date is 2015 because that's when the Paris Agreement was signed. So notwithstanding the very mixed, to put it mildly, success of the last 20 years vis-a-vis greenhouse gases, Paris was very ambitious. And I just want to give you some quick context on that. You can look at it on your own time, but importance of biological feedbacks, the recognition that damages are higher than expected, pollution has retarded warming, but the effect of retarding warming is decreasing. So that means that there will be added warming from reducing aerosols, which is very important on its own terms, but it'll have an effect that's unaccounted for if you just look at greenhouse gases on warming. Collapse of ice sheets can raise sea level faster than thought. Understanding of intense events, faster shrinking of ice sheets and Arctic sea ice, long atmospheric lifetime of CO2, extreme events, irreversibility, right? And this is often, these diagrams are often called the burning embers diagrams, and they're often used in these synthesis reports to just summarize the collective view of the community. And the reds obviously mean more bad things can happen at lower temperatures. And note the big difference between in 2001 versus 2009, the distribution, right, of where the yellows and the reds rise. And also vis-a-vis this, right, net negative in all metrics, right? And also here, negative for most regions. We're finding that more regions are going to be affected. And this comes from climate science, but at the same time, there's a lot of uncertainty. And if you look at, what this means for decarbonization goals, you often see these shaded bands, and that comes from uncertainty in not only the equilibrium response, but also the transient response that have been alluded to in the previous talks. And for any mitigation trajectory, you're going to have necessarily a distribution of impacts. And that's why things are ultimately probabilistic. And so we know a lot about impacts, but any characterization of what this means for our mitigation ambitions is going to have to be couched in probabilistic terms. So this is just another representation of that from work that's been very influential in the community. I also want to briefly discuss this point, and you may have noticed sometimes when people describe probability distributions of climate sensitivity, they essentially have a fat tail. And this is another feature that has been recognized not only in the climate science community, but also in the economics community over the last 15 years. And that essentially comes from transforming probability distribution. So essentially you have a delta T naught in the absence of feedback term F. And if F is 0, your global warming, equilibrium global warming will be delta T naught. If you have a non-zero feedback, which is positive, right? Those of you that have taken a class in controls will be quite familiar with this. Delta T is larger than delta T naught, and F is the normalized factor that lies between 0 and 1, right? But positive. And so then if you look at the relation between the probability distributions of delta T and F, right? You can have a normal distribution of F, but a fat tail distribution of delta T. And this also evokes broader questions about how we build ensembles, how we reduce uncertainties, and so on. There's a much deeper literature here, but the basic point is it's possible it has a fat tail, especially if the feedbacks are symmetrically distributed. Then you're going to have an asymmetric distribution of climate sensitivity. And there's a famous result in economics by Martin Weitzman, who, when these early results were coming out about 15 years ago, some economists also started to say, what does this mean for uncertainty and losses in economic damages from climate change? And this is a dismal theorem. I'm not going to state the dismal theorem. It's received the status of a theorem. I would say it's important, but I would qualify it. I think there are still many questions about whether we can do better and constrain, right? And a lot of the recent literature on emergent constraints and understanding, bounds from physics on climate sensitivity and on prior distributions that you put into these probability calculations has much more to say about circumscribing our uncertainty about climate than these discussions would suggest. But I think the economics community has begun to come to terms with what this means for economics. A fat tail has the potential to dominate economic calculations. Analysis of a situation that might potentially be catastrophic cannot afford to ignore tail behavior. It's not enough to just look at central tendency at thin tail probability distributions. Ignorance of the potential fatness of an extreme bat tail is not an excuse for ignoring the potential fatness of an extreme bat tail, right? So ignorance is not an excuse for ignoring the potential fatness. The fact that we cannot constrain the extreme part of the distribution doesn't mean we should not pretend that we're ignorant about its possibility. I think that's the message here. And this warning is the main message of the Dismal theorem. And it's received a very, there's a section of the economic community that's taking uncertainty into account, also to a great extent influenced by these kinds of results. Another feature is, you think about the social cost of carbon, it tends to be larger in warm countries. And if you're interested, you can ask me, we can discuss that. But as the studies of social cost of carbon have proceeded, here's a recent review from this year. The x-axis shows the year of publication, and the y-axis shows the distribution of the social costs of carbon. And this is when we started to get the science, and some of the economics to understand this. And as time proceeds, the distribution of the social cost of carbon seems to be shifting to higher values. Another important fact is the global social cost of carbon is much higher than the mitigation costs, which also have been declining, especially in the renewable energy sector. And here's another important paper from this year, which increasingly has begun to say, well, it's very hard to quantify the economic impacts, and many of these things are profoundly important impacts that can't be quantified economically, right? For a variety of reasons. The relevant markets may not exist, the relevant shadow prices may not exist. Let's start asking, what is the scale of population affected around the world by various things? And so this just came out, I think, a few weeks back, and it shows for various quantities such as the mean annual temperature, the wet bulb temperature, which imposes limits to physiological adaptation, sea level rise, and also multi-century sea level rise. Because what's the important reason for distinguishing these two? Because sea level rise is, you can think of it as integrated global warming, right? Sea level rise is a long-term phenomenon. And so even if global warming were to stop, sea level rise won't stop, right? Sea level rise will continue. And so a zero-thought model for global warming is it's proportional to integral of cumulative emissions. Likewise, a very simple model for sea level rise is proportional to integral of global warming, right? So the double integral of emissions. And so in each case, you see a large increase with temperature. You can also see there's a difference between 1.5 and 2 degrees, all right? So, and I'll conclude with this very important point. Again, it came out in a very recent paper by an economist calling for a change in climate, in climate economics to accommodate the reality of climate change, but also our change in understanding, right? So broadly speaking, I would say about 20, 25 years back, it was about economic optimization. How do we trade off economic growth versus pollution, right? That was the kind of question. Now, with all the new climate science that's come in over the last 25 years, people have realized that's not the right way to think about it. The stakes are far too high. And so the role of economics has to change. It's how do we cost effectively navigate a transition that has to be done, that's not the outcome of solving an optimization problem in economics, right? And so I think it's worth reading this in its entirety. Madhava's question, recognizing that there could be potential dangers from climate change, emissions arose from activities around producing and consuming, was should we grow a little less fast than we might have envisaged before we thought about climate change? Right? He proceeded in a sensible way for his time, taking an emerging problem, applying the standard tools of economics. First, the story, Pigou was the one who pioneered thinking about how to tax pollutants and so on. So by this story, he's referring to basically Pigou's ideas about adding a tax on things to internalize externalities, taking an emerging problem, applying the standard tools of economics. First, marginal social costs, marginal private costs, taxing for the externality, and use the framework of exogenous growth model and considered impacts, largely in terms of small perturbations around the underlying growth paths. Right? That was a sensible and valuable early contribution for the economics of climate change. And over the following 10 to 15 years, it became more and more clear that climate change is not a marginal problem. We're dealing with a challenge involving huge potential disruptions. Rising to the challenge requires radical changes in our production systems and ways of consuming. This comes from an economist. Their scope has been expanded, but the underlying features of optimization of explicit calibrated social welfare functions, of underlying exogenous growth, and of aggregation impose severe limitations on their ability to illuminate two basic questions. First is how to approach analytically the challenge of managing immense risk, which could involve loss of life on a massive scale. Second is how to chart and guide a response to this challenge, which will involve fundamental structural change across the whole complex economy. Right? And far be it for me to add anything to this, I'll stop here. Yeah, thank you. We'll take questions.
There is maybe time for a couple of questions. So if you have a question, please.
So in all the scenarios that you plotted, why are all the carbon emissions going down to zero? Except I think one blue line was...
It's a supposition. Scenarios are essentially suppositions, but they're not predictions of how the world will play out. Let's suppose so that we can then run it through a model.
All right.
Yeah.
Thank you.
Yeah.
Any other question? I have a slight generic question.
Yeah.
All these climate models we are using for impacts are actually derived products or the products from the climate models. Let's say I'm just referring one product as wind.
Yeah.
So every model gives different products. And when I want to evaluate for wind, I may get specific product which seems to be giving a better output. Mm-hmm. But when we look at some other output, there could be some other set of models which may be giving a better output.
Yes.
So in general, when we want to take models for various applications or various use or model outputs for use, should we again evaluate for specific parameters and then use, or is there some kind of guideline in your knowledge or anything that is available?
I don't think there's an answer deductively from first principles. I think this is a matter of partly a matter of taste, but mostly, I think, a matter of judgment, and also partly a matter of luck, because I think luck plays an important role, because we can't be sure, if you only evaluate models based on wind, that you may not be sub-optimizing, given that in a non-stationary context, something else might matter, which is poorly represented. And there's no way to know that, right? So given that our ensembles are very sparse ensembles of convenience, I think there's an element of luck that I don't think we should. But it seems rational, sensible. If you're doing wind, of course you want to represent the wind well, right? But among those that represent the wind well, do you use all of them? And I think maybe a good strategy is just characterize uncertainty. So if you have, if the model's rendition of wind is garbage, then you won't use it. But among those that are good enough, it's not necessarily that the best one will be the best one in the non-stationary context.
Right.
So maybe use all of them, characterize uncertainty. Yeah.
Okay. Okay.
Yeah.
Thank you so much.
Yeah.
Thank you. In the interest of time, maybe let's take the question during the lunchtime. I think Ashwin will be available. Also in the afternoon. So let us thank Ashwin again for very nice talk.